Hello and welcome back to the tutorial in Commonsense knowledge extraction and consolidation. And we are going to section 4 on text extraction. So text extraction is a topic of long attention in knowledge-based construction and natural language processing. The fundamental idea is to exploit patterns or commonalities in natural language in order to extract knowledge. So if you have a sentence like lynx eat hares and elephants eat grass, then what do these sentences have in common? Well, they link a subject and with an object that it consumes. So we could derive here the pattern that blank eats blank implies this relationship. And fundamental design points for text extraction for common sense knowledge-based construction are the choice of sources, the choice of the extraction method, and the choice of the consolidation scheme. And we'll discuss each of them in more detail and at the same time review prominent projects, in particular WebChild, TupleKB, Quasimodo, and DOQ, distribution over quantities. So design point 1 is the extraction source. And popular sources that have been used there are Wikipedia, very popular because it's high quality, little noise, to some degree reasonable homogeneous writing style, focusing on general world knowledge, good coverage, and so on. For that reason, quite popular. Another popular sources are books and other dedicated sources. For example, there's an ARC science corpus used a lot by the Allen Institute of AI, which is websites or books dedicated to science knowledge, which again gives high quality topically relevant texts. Then towards the noisier end are web crawls. So popular used their ClueWeb and Common Crawl. Advantage of them is the size, so there's more chance to observe things multiple times to exploit redundancy. On the other hand, there's a lot of noise and huge variety in the kind of language. The middle ground here is doing targeted web search, so using the general web, but then posing specific search queries that have the chance to return more targeted content. Another source we see used are forums, for example, Reddit and Yahoo Answers, with the advantage that one can again target specific topically relevant forums. And finally, search engine query logs are used in the Quasimodo project, which we'll see are a very good source for salient knowledge. The second design point is the extraction scheme. So starting with the simplest, the extraction scheme are manual patterns, for example, Hurst patterns. Manual defined patterns like X eats Y or so allowed to extract simple relationships. More relaxed extraction schemes are just co-occurrence. So Yago and DOQ use that. So let's just look whether a subject and an adjective or a quantity co-occur within a certain window or within the same sentence. Take that as a signal. Open information extraction is a popular scheme. Open information extraction essentially targets verb-mediated expressions, any kind of expressions. And then we can also go to relation-specific supervised learning. So if we have training data, we can learn extraction patterns for each relation separately. And the third design point is the consolidation scheme, where the simplest is to do nothing, so to keep everything that results from the previous phase. However, often there's a substantial amount of noise among extractions. So a simple consolidation scheme is frequency cutoffs. For example, keep all statements that were seen at least 5 times. Then more complex consolidation means we can, per statement, try to consolidate statements, cluster them, use features in a supervised model or unsupervised rule-based cleaning of statements, or we can do a joint consolidation of various statements. We'll go in detail in that in section 6 of this tutorial. So let me now delve into exemplar projects. So the first I want to present is WebChild, developed in 2014 by Tandon et al. And it's among the first large-scale attempts at text extraction for common sense knowledge. So it is named after the idea of reading the web like a child, or getting the web as clever as a child. And the original focus of the project was linking nouns with adjectives. So which adjectives apply to a certain noun. And it was later extended to other kinds of knowledge. But I'll stay with this initial idea of nouns and adjectives. And as text source, it used a Google 5-gram corpus. I think it's Google Books actually. And about 20 manually defined patterns. So a few copular verbs like be, look, feel. So apples look colorful, or sport feels fun, or similar verbs. And the key ideas of WebChild are to get fine-grained relations for common sense knowledge. So we don't just want to know that an adjective applies to a noun, but we want to say in which relation they stand. So is it about the appearance, or the taste, or the temperature, or the shape, or similar? And the second idea is to disambiguate the meaning of adjectives, because adjectives can be overloaded. So hot can mean a taste, or a temperature, or an appearance. We want to disambiguate them to word senses in WordNet. So here indicated by the superscript. So the adjective hot has 9 or more word senses in WordNet. And an approach of WebChild is given a generic extraction like salsa has the property hot. So this shall be refined in the statement that which salsa is meant. Is it the sauce or the dense? Then has properties refined into one of 19 relations. Here the taste, and hot is refined into the sense number 9, which is the spiciness of food. And the steps to get there are first to populate the range of relations, second to populate the domains, and third to compute the actual assertions. So we start on the right-hand side of this slide. Given the has-taste relation, we want to know what are the possible values for that relation. So it's spicy, hot, sweet, and others. Then we want to know what are the popular subjects that have a taste. So for example, pizza, sauce, Java, not the language and not the island, but the coffee. And then we want to compute the actual assertions. So that chocolate has taste sweet, that milk has taste tasty, and so on. And the approach for the first and the second problem for the range and domain population is to get a large set of potential candidates for the relation, and then construct a weighted graph of words and their senses, label a few seed nodes, and then use label propagation in the similarity graph to denote which nouns and adjectives qualify for the range and domain of a relation. And for computing the actual assertions, the idea is to use a range and domain to prune the search space, and then again use label propagation from similar assertions. So here we see an example graph. So we have on the left-hand side the ambiguous surface forms, sauce and salsa. On the right-hand side, we have their senses, so the salsa dense, the salsa sauce, then the general sauce. And the edges that are used to populate this graph are taxonomic edges. So the salsa is a sauce. This is the edge with weight 0.8 on the right here. Then co-occurrence statistics in a large textual corpus. So that the words from the salsa dense co-occur with the term salsa, which gives us basically the prior probability. And then distributions between words and word senses, using here the WordNet glosses, which disambiguate word senses. So we can see that the salsa and the sauce co-occur a certain number of times. And then this can be fed into a joint optimization problem where in blue we have known positives. So a shake really is in a domain of Hess taste. A sweet is really in the range of Hess taste. We can do label propagation to identify other objects in domain and range of the Hess taste relationship. And we have some known positive assertions, which come again from the WordNet glosses, so that shakes are indeed sweet. And then we can propagate these positive labels to other similar statements. And here are examples from Webchild's resulting statements. So what is in the domain of Hess shape? So faces and leaves have a shape. What is in the range of Hess shape? Well, shapes can be triangular or tapered. And what kind of assertions for the Hess shape relation are there? So for example, lenses are spherical or palaces are domed. And Webchild can be used for here we see examples of top attributes of the keyboard. First as the computer keyboard, second as the one where you hang your keys. And we see this really makes sense. So a keyboard can be, the computer keyboard can be ergonomic, foldable, black, lightweight, waterproof, and so on. Whereas at the bottom, the keyboard where you hang your keys can be magnetic, decorative, and so on. And one can also use this knowledge base to do set expansion. So given the subject, which other entities share similar properties, and so we see that the sets are very different. So USB keyboard, computer keyboard, QWERTY keyboard, and so on, versus wall mount, wooden frame, and so on. And so in summary, graph methods help to overcome sparsity of common sense in text, and Webchild is the first common sense KB with fine-grained relations and disambiguated arguments, in total over 4.6 million assertions for 19 relations. And its precision was also sampled and found to be 0.8 and higher. With that, let's move to the next knowledge base. Tuple KB is a project from 2017 at the Allen Institute of AI. And the focus here is on knowledge about science topics. And the main ideas are for the sources to use direct web extraction via a search engine. So there are manually authored query templates used to extract the relevant websites for the subjects. For the extraction scheme, the idea is to use an open predicate set via OpenIE, which is later partially clustered. And for consolidation, a supervised scoring is used for supervised prediction model. And here we see the pipeline of Tuple KB. So given from a corpus of websites returned by a search engine, relevant sentences where entities of interest are the subjects are extracted. OpenIE is run on them. Statements are scored by a supervised model based on crowd annotated statements. And then there's a canonicalization stage where irrelevant modifiers are dropped and relations are canonicalized based on word senses and similar, so that in the end, the generic relation have, we see here at the bottom left, leaves have chlorophyll is refined to the more specific relation, leaves contain chlorophyll. And notably, Tuple KB evaluated not only its precision, precision found to be quite high, 81%. But notably, they looked also at recall, and that's an interesting problem because evaluating recall of common sense KPs is typically a hard problem. So how can we say how much of the common sense knowledge we have? And their idea was they took sample text from 4th grade science books, manually coded the statements that were expressed in these sentences, and then checked how many of these statements were in each knowledge base. And so they found a reasonable coverage of 23%. So about a quarter of the statements needed for 4th grade science are contained in tuple KB. Okay, with that, let me move on to the next project, Quasimodo. Again, quite a different focus. So the title stands for Query Logs and QA Forms for Salient Common Sense Definitions. So the focus here is on salient knowledge. So not just knowledge that is true, but also human that knowledge that humans find interesting, that raises the curiosity. And the characteristics of this approach is, again, an open IE schema like tuple KB, a careful choice of sources and utterance context, we'll see in the next slides, that gets a handle at salient knowledge, and a supervised corroboration stage where multiple sources are merged. So let me briefly review previous works. What are the shortcomings? Why this work on saliency? So ConceptNet, done by humans, has salient statements. It has what humans find interesting because it's done by humans, but it has a low coverage and it's quite idiomatic. So we've seen earlier here, elephant is capable of forget to go on the paper or visit the grocery store. These are weird idioms, which I don't know where they come from. And there's also redundancy. So elephant lifts the tree, lifts logs from the ground, carries a trunk, which would preferably merge. On the other hand, the automated extraction approaches, WebChild and tuple KB, have a higher coverage. However, they are incoherent and have incomplete statements, and especially ugly is salient is not really taken into account. So in WebChild, we find adjectives that can apply to a hyena, so small, large, demonic, fair, and a lot more, 73 adjectives. But now what is true? Are hyenas small or are they large? That's somewhat contradictory. And tuple KB has generally good statements, but some are somewhat incomplete. So elephants require ground. Okay, what kind of ground? What for? Inhabit region. What kind of region? And Quasimodo tries to address these aspects. So the key idea of Quasimodo is that questions convey salient knowledge. So if you ask a question like, why do cats purr? Why do Americans love guns? Or why are airplanes white? Then this conveys two things. So A, someone knows these statements or beliefs, holds these beliefs, and someone cares enough, wonders enough about them that they ask the question. If I ask, why are airplanes white? Then this puzzles me actually. And so the idea of Quasimodo is to use primary sources on questions, QA forums like Reddit, Quora, Yahoo Answers, and search engine query logs, in particular Bing and Google. And search engine query logs are normally a well-guarded secret that we don't easily get access to. But the idea of Quasimodo is to get an indirect access via auto-completion. So if you go to a search engine and type, why do cats? You get interesting completions like, why do cats purr? Why do cats like boxes? Why do cats meow? And these are almost perfect assertions. So cats purr, cats like boxes, cats meow. These are salient statements that people know about cats. And yeah, typically auto-completion gives only an order of 10 suggestions. So then there's a recursive probing. Why do cats A? Why do cats B? Why do cats C? And so on until there are no more suggestions. And this is done for a variety of patterns. How does, why is, how do, why do, and so on. Thus achieving quite impressive coverage of questions. And given the actual questions, like why are lions hunting zebras? This first with simple lexical rules translated into a statement. So lions are hunting zebras. Then open information extraction is applied, getting a triple like lions, are hunting, zebras. And soft normalization is applied to get rid of the R. So lion hunt zebras is the resulting statement. And so here we see anecdotal examples from Quasimodo, which cover quite a range of human knowledge. So that cars slip on ice, that pens can leak, that divorce can hurt, that ghosts scare people. Also comparative knowledge that light is faster than sound, and so on. And for Quasimodo, both the precision was evaluated in a fine-grained manner for 3 dimensions. So how meaningful are the statements? Can we comprehend at all what that means? How typical is the statement? And how salient is it? So in blue, we see Quasimodo scores compared with the other automatically constructed resources, WebChild and TuppleKB. It outperforms them in all regards. The manually constructed concept net still is better in these 3 dimensions. However, its recall is much lower. That we see on the next slide. So the recall was calculated again by getting human expectations. So workers were asked, tell us 3 things that come to your mind when thinking of lions, like lions live in Africa, lions roar, lions are big predators. And then it is checked how many of the statements that humans come up with are contained in a knowledge base with slight reformulations. And here Quasimodo by far outperforms both the automated and the manual concept net. There's also an extrinsic evaluation of the strengths of Quasimodo using a simple question answering setup where the connectedness in terms of statements between answer options and question is checked. So Quasimodo generally scores best among the structured resources here. Quasimodo still has various issues. So one issue is that questions sometimes go towards the odd. So you ask a question when you have a problem, especially for everyday appliances. So for a car, you ask, why does a car leak oil, catch fire, not start? You wouldn't ask, why do cars transport people or consume fuel? So the very obvious statements are not always found by this extraction scheme. And another issue is how to fit a longer phrase into triples. So lawyers can make the world a better place or are good for a fair and judicial system. These are natural language sentences, but they somewhat go beyond the triple model of lawyer has a simple property. So much about Quasimodo. Then last, let's look at quantities. So quantity understanding is important in question answering. For example, if you want to know what is a fast but expensive way to send small cargo, is it a ship's hold, a boat, or an airplane? Well, if you know that ships are slow and airplanes are fast and expensive, we could perfectly answer this question. These qualitative assertions, fast and slow, are somewhat captured by WebChild. However, they are limited, reliable, and comparable. So what DOQ, distribution over quantities, aims at is to understand numerical properties and get the actual quantities out of texts. And this is recent work by LSR and others, ACL 2019. So the focus of this work is on the measurable world, so things which can be objectively measured, like speed, length, or weight. And the approach is a quite simple one, looking purely at co-occurrence of measurements with words in their context, in a context window, using a very large text corpus. And that this can work, so here's a simple example, a qualitative example, again looking at a large text corpus, Google Book Ngrams over time. What's the relative frequency between fast train and slow trains over time? We can see an interesting pattern here that so over time, trains were more and more considered fast until the 1900s. In the 1900s, what happened? The airplane was invented and also the car became more widespread. And since then, the fast trains have declined again in frequency compared with the slow trains. So today, trains are not considered so much fast anymore. But let's go back to the actual quantities. So what is the technical approach? Given a sentence like these breeds can vary in size and weight from a 0.46 kilogram teacup poodle. The first step is to detect numerical measurements by a set of rules, so like kg is kilogram, which indicates that the quantity type is mass. Quantities are normalized, so here into grams. Then objects of interest, in particular nouns, adjectives, and verbs are detected, so breeds, size, weight, teacup poodle as a noun phrase. And then disregarding the very general terms like size and weight, we can say that breeds for the quantity mass, we've observed 460 grams, and poodles for the quantity type mass, we have observed 460 grams. This way we can create a huge dictionary of observations for each noun, and we can plot the distribution. And what we get here, for example, are these plots. So for a car, the speeds we observe starting from 40 kilometer per hour up to 250 kilometer per hour, with a peak at around 100 kilometer per hour. And an electric car has a slightly wider range. A luxury car has a shift towards higher speeds, the race car even higher observations. We also see that this works for temperatures over months. So the temperatures we observe over different months really show a typical pattern as we would expect on the Northern Hemisphere, that June, July are the months with the highest temperatures observed, and December and January the ones with the lowest. And so the resulting resource is called DOQ, distribution over quantities, is a really huge resource, about 120 million unique tuples of an object in the measurement. 250,000 objects have more than 1,000 occurrences. There are 27 measurement types in total, like length, mass, currency, temperature, and so on. And the resource has a quite reasonable quality. So to evaluate it, the authors looked at the median of distributions, expanded it into a range, and asked annotators whether this made sense. So is the usual length of a screw between 10 and 100 millimeters? And agreement was 70%, which is not perfect, but which is a reasonable start for a difficult problem of quantity annotation. And the results are actually quite impressive. So here's another example of speeds. Ship is usually a larger thing than a boat, so boats are faster. Trucks are slower than cars. Also for time, so for the hour of day, for breakfast, we see 8 and 9 are very popular. For brunch, it's much later, 11, 12 until 2. Lunch, even a bit later. Dinner has a quite a distribution, but peaking around 6 p.m. and so on. Nonetheless, there are some issues. So for example, for C, the results were quite odd. So if you go for C, and what is the length of a C, there's a peak just close to 0. So what is the issue? There are a lot of sentences saying the elevation ranges from 3,000 feet above sea level. So this pure co-occurrence doesn't take into account that this doesn't talk about the length of the sea, but about something very different. Or another example is alfalfa is the most cultivated legume, reaching around 454 million tons. This is of course not the weight of one alfalfa plant, but this refers to annual production, and so the weight of alfalfa is totally off as we see here. Nonetheless, the results are quite cool. So here's a case study of temperatures collected for US states. So what is the real average from meteorological observations, and what is the mean predicted from the DOQ resource? And we see a great correlation between the colder northern states and the warmer southern states in the US. To summarize, DOQ is a very simple method for collecting measures. The resulting resource is huge and has a encouraging quality for various downstream use cases. So let me summarize the text extraction part. So underlying all text extraction are design choices of the resource, with a question of redundancy versus quality typically. The choice of a data model, so do we want normalized statements or not, and the choice of an extraction scheme, so do we use supervised learning for a limited set of relations, do we use open information extraction, do we use mere co-occurrence, and what we'll see later on, how do we consolidate statements. And here I've listed major resources, also some earlier works that I didn't discuss now. Thank you.